Hello everyone, I'm Thodoris and I'm a PhD student at the Athens University of Economics and Business. I'm going to present our work titled A Model for Detecting Faults in Build Specifications. This joint work with Stefanos, Chaliasos, Dimitris, Mitropoulos and Professor Diomidis, Spinellis. Automated builds are an integral part of software development. Someone can run into a plethora of build systems whose goal is to provide developers with efficient builds while preserving the reliability of software artifacts. To do so, they provide crucial features such as incrementality and parallelism. Through incremental builds, the build system processes only those build operations that are affected by a particular change in the code base. To enable incremental builds, developers need to specify the complete list of input files of every target file produced by the build system. For example, in the make script shown on the left, we can see that the developer specified that the input file of qualitrymedics.o file is a header file named qualitrymedicsnames.h. For parallel builds, the build system processes unrelated build tasks in parallel for achieving a better performance. For example, by examining the dependency graph shown on the right that shows the dependency relations between different build tasks, we infer that make can translate every individual source file into the corresponding object file in parallel, and after these individual compilations, it can invoke the linker to create the final executable. Developers need to be very careful to specify the correct dependencies among dependent build tasks. For example, build tasks that produce a file need to proceed the execution of every other task that consumes the same file. Incrementality and parallelism can pose threats to the reliability of the build process if they are not used correctly. Here we see a make script that manifests an issue related to incremental builds. Here the developer specified the GCC option -md that creates a dependency file containing the input files of every object file generated by the compiler. The developers include the generated dependency files into their specification using the include directive. The issue here is that the variable ops does not take into account the object file name qmcal.o. As a result, if we update a file on which this object file depends, make won't regenerate the corresponding object file. And as a result, the final executable is linked against stale object files. We name this issue as missing input, and similar to missing inputs, we have missing outputs. This time, developers fail to enumerate the output files of every produced by a particular build task. Let's proceed to ordering violations. An ordering violation issue is related to parallel builds. Here we have a simple build script written in Gradle. Gradle is a modern build system which is particularly used for building projects written in JVM programming languages such as Java, Groovy or Kotlin. Here, this script contains two tasks. The first task is named jar and creates the jar of the project, while the second one is named shadow jar and creates the fat jar of the project. A fat jar is a jar file that beyond the class file of the project, it contains the class file of project dependencies. These tasks do not depend on each other, so Graal is free to execute these tasks in any order. So at the end of this build, we can end up with a jar file that is not a fat jar as intended if Graal executes the jar task after the shadow jar task. Faults in incremental and parallel builds can cause various issues including build failures, non-deterministic build outputs, stale artifacts, and many more. There is prior work that tries to detect these issues, but it only targets make-based builds and it suffers from two fundamental issues. The first fundamental issue is related to low precision. Imagine that we have two build tasks, A and B. Task A consumes file A.in and produces file A.out, while task B consumes file B.in and produces file B.out. The previous approaches work on granularity of system processes, and they assume that the build system always spawns a separate system process every time it proceeds to a separate build task. An example of a build system that works in this way is make. So the previous approaches, when they are applied to make builds, they are able to correlate the correct input files with the correct output files, because they are able to distinguish the different build tasks from each other by tracking every system process along with the files read and written by every system process. However, there are build systems where the same system process handles different build tasks. In such build systems, the previous approaches merge the build tasks governed by the same system process into a single task. So we have loss of precision, and imagine that we update the input file named A.in. The previous approach is considered that both output files need to be updated, even though only A.out depends on the updated input file. Another fundamental issue is related to efficiency and applicability. Prior work reasons about only OO's level facts. They track system processing and their file operation. So we need some way to verify these facts against the static build specification written by the developers. One way is to perform incremental builds, that is, we update an input file, we trigger an incremental build, and check whether the build system updates the expected output files in response to the updates. However, this is not very efficient because every time we trigger incremental builds, so a workaround is to perform static analysis on build specification. A particularly challenging task because some dependencies are only known at runtime because they're computed dynamically. To address the limitation of the previous approaches, we propose a model for arbitrary build executions named BuildFS. The key insight of BuildFS is that it provides us with both the static specification and dynamic behavior of build tasks. Through BuildFS, we treat a build execution as a sequence of build tasks. So BuildFS tackles low precision because now a build is modeled as a sequence of tasks rather than a sequence of system processes. So every file operation is associated with the task it comes from. And of course, this works for every build system regardless of the internal behavior, i.e. whether they spawn a separate system process or not. BuildFS also tackles efficiency and applicability because the model incorporates both the static specification and the actual behavior of each task. So we don't need to perform static analysis on build scripts or trigger incremental builds to decide correctness. To evaluate a build execution model in BuildFS, we have a state that mimics the file descriptor table of Unix-like operating systems, and the evaluation of a BuildFS task on state sigma gives us a new state sigma and an instance of the domain of file accesses. This domain gives us the set of files consumed and produced by the task. We also introduce two relations. The first relation is called subsumption relation, which is a binary reflexive relation between two paths that says whether one file is included within another. For example, if we have parent-child relationships between files. And the second relation is called happens before, which is a binary relation between two BuildFS tasks that says whether the execution of one task precedes the execution of another. Based on these relations, we introduce the property of correctness. Let BuildFS tasks, we say that this task manifests a missing input on state sigma if we evaluate this task on state sigma, and this task consumes a file for which the subsumption relation does not hold with respect to the specification of the task. We have similar definitions for missing outputs, and finally we say that this task is correct on state sigma if it does not manifest a missing input or a missing output on state sigma. For ordering violations, we presume that there is an ordering violation between two tasks if these tasks have conflicting file accesses and the happens before relation between these tasks is not defined, meaning that they can be executed in any order. The testing approach that relies on BuildFS is shown on this diagram. First, we monitor the execution of an instrumented build script and we model this execution in BuildFS. Based on BuildFS semantics, we evaluate every BuildFS task to compute their file accesses, and the final step is fault detection, where we check whether there is a file access that violates the property of correctness, again based on the definitions of BuildFS. The instrumentation performed on build scripts has two goals. The first goal is to provide us with the execution binaries of every task so that we can map every file operation to the task it comes from. The second goal is related to the specification of the task as specified by the developers in the underlying build scripts. So for this purpose, we place instrumentation points before and after the execution of every task, and we augment their execution by calling native function holding the above information. We benefit from extracting the specification at runtime because first, we don't need to perform static analysis on build scripts, and second, the build system has the complete knowledge of the specification at runtime in order to perform a sound execution. Some implementation details regarding the instrumentation. We have added support for two well-established build systems, namely make and Gradle. For make, we have created a simple shell script that wraps the execution of every make rule and dumps the prerequisites of this rule to the standard output, while for Gradle we have created a simple Gradle plugin that hooks before and after the execution of every Gradle task and provides us with their dependency information as described earlier. The developers need to put only these 3 lines of code into their scripts to enable instrumentation. So adding support for a new build system is fairly easy and straightforward. All you have to do is to implement the instrumentation. The implementation for make consists of only 8 lines of code, while our Gradle plugin contains roughly 90 lines of Kotlin code. We have applied our method to 612 Gradle and make projects taken from GitHub and Debian ecosystems. For Debian make projects, we use dsbuild Debian utility that guarantees the reproducibility of Debian binary packages by automatically installing all B dependencies in isolated environment. Our method was able to detect hundreds of issues in both Make and Gradle projects. Most notably, 247 issues found in 47 open source projects have been confirmed and fixed by the developers. Here is an interesting case study taken from an open source Gradle project. The script here defines a task named generate nodes that creates some Java source file at build time. This script also defines a task named source_jar that assembles all source file into a jar file. If Gradle executes this task in the erroneous order, we can end up with a jar file where the source file generated by the generate nodes task are missing. Regarding performance, the instrumentation slows down build by almost a factor of 2. We also compared our tool with a state-of-the-art tool for make builds, namely mkcheck, and we found that BuildFS is 4 orders of magnitude faster than mkcheck in detected faults on average. BuildFS is also 74 times faster when considering the overall times, that is, the time spent in building the project plus the time spent in detecting faults. These numbers are justified by the fact that mkcheck triggers incremental builds for deciding correctness, which is not very efficient. To conclude, we have introduced a general applicable method and model for detecting faults in incremental and parallel builds. To demonstrate applicability, we have applied our method to both traditional and modern build systems, and most notably our method is the first to handle JVM-based builds. The experimental results indicate the effectiveness of our approach as we were able to discover hundreds of issues. Thank you for listening.